So previously we have defined a notion of homological equivalence on divisors. If X is a complex surface, then we can view the Weil divisors as two-dimensional cycles. So two divisors are homologically equivalent if and only if their corresponding cycles are homologous. Well, this notion is very nice and geometric, but the problem is that would only work for surfaces over C. And as we said, we are doing algebraic geometry, not analytic geometry, so we want to extend this notion to work for more fields. And that will lead us to the notion of algebraic equivalence. To this end, let's review what it means geometrically for two chains to be homologous. Right, let's just look at the case of simplicial complexes. Remember, two chains of the same dimension are homologous if they form the boundary of a chain of a higher dimension. So for example here, A and B are a chain of dimension 1, right? And the difference A minus B form the boundary of this two-dimensional chain. Now, to be able to generalize this notion, we need to rephrase it somehow in a way that it's more algebraic. Instead of viewing A and B as this boundary of this two chain, we now want to view them as varying in a family. Right, so they're connected together by a family. So maybe we could define two divisors to be algebraically equivalent if they are both part of the same algebraic family of divisors. They are algebraic equivalent if they are algebraic siblings. Alright, so what is an algebraic family of divisors? Well, all the divisors in this family must live in some space, right? So to define the notion of a family of divisors, we probably need first a family of copies of X. And that's way more intuitive, right? So we can have a family of copies of X varying over some base. What does it mean? Well, we take some algebraic variety, S, as a base, and then a family of X is just what you think it is. It's gonna be this product, X times S. So over each point S, of big S here, we have a fiber that is a copy of X. Right, this is X. Alright, so now what should the definition of an algebraic family of divisors be? You might say, well, over each point S here, I pick a divisor in the fiber. This is divisor on XS. Right. Well, that will give you a family, I guess, but there's nothing algebraic about it. There's no relationship amongst these different divisors, right? We want the divisors from fiber to fiber to vary in a way that is algebraic. So we will require that the totality of all of these divisors on each of these fibers, their totality, their union, is actually a divisor of this product space. In other words, an algebraic family of divisors on X with base S is a divisor of X times S with condition that it should never fully contain any of these fiber XS. It should not contain the whole XS, so that its intersection with each fiber XS here is a proper divisor of XS. And now we can define algebraic equivalence. Two divisors are algebraically equivalent if and only if they are connected by an algebraic family of divisors, if and only if they are algebraic siblings. It turns out that when X is a surface over the complex numbers, then these two notions are equivalent. So that means this algebraic equivalence is actually a true generalization of this homological equivalence. It's not just an analogy. Now that we have had a notion of equivalence, we have to do the next proper thing, which is to form a group. So we define the Néron-Severi group to be the group of Weil divisor modeled by algebraic equivalence. It turns out that this group is finitely generated, and its rank is called a Picard number. That's an important invariant. And remember, we mentioned that for surfaces over complex numbers, the algebraic equivalence notion is the same as homological equivalence. So this map then induces an injection from the Néron-Severi group into this two homology group. In particular, this means that the Picard number has to be less than or equal to B2. The nice things about the Néron-Savary groups is that when we look at this group, we can just bypass any continuous deformation of curves, and then we get to work with a discrete group. In the next video, we're gonna do some computations of Néron-Savary groups.